Yeah, actually you pronounced my name perfectly, thank you. Hi everyone, welcome to my presentation. Today I'm going to talk about the Tesenas, which can appear in automation environments, and possible solutions against them. And let me first introduce myself. My name is Mesut Durukal. I'm from Turkey and I'm working in Siemens Istanbul office. And I'm a test engineer for 11 years, during the presentation or afterwards, please do not hesitate to reach me out for questions or recommendations. And this is the brief agenda for today. First, I will start with some introductory information, and then I will talk about what a testml is and possible testml types defined in the literature, and finally I will go over one by one the solutions that we applied to solve the problems stemming from the testmls. So I will talk about the system under test from the project which I was involved in and our test automation environment, just to give some ideas about the environment and give some insights about the environment. But normally what I will talk about the testmls and the solutions are not case-specific ones, and they are generic testmls which can appear in any automation environment. So the system under test in our project was the Myspare, which is a product developed in Siemens. It's a cloud-based open IoT platform. And in this product, you can connect your devices to the sensors in the field to collect data from the field and upload them to the cloud. And in this way, you can monitor, store and manage your data in the cloud. In this way, you can visualize what's going on in the field and what's going on in your manufacturing lines. In addition, it can be used as a development platform. It means it's a platform as a service as well. And you can develop your own apps and deploy them to the cloud. And you can do all this by using the open APIs and UIs of the system. So as a QA team, what we do is to test these open APIs and UIs of the system. And it's a big product actually, developed by more than 10 sites, I think, globally distributed sites, and by more than 600 developers. And there are almost 30 services in the product. And there are around 300 microservices inside. I especially wanted to show this image because it's a pretty lovely product from outside, but inside it has a complex structure. The architecture is built upon a microservices concept. It's chosen because it has some advantages. It promises for some flexibility opportunities. But on the other hand, all those microservices are working asynchronously, they are working independently, so there are some drawbacks and difficulties, especially in terms of testing activities. And this is the automation environment for our testing activities. We implement our test cases to automate them, and then we are executing them periodically or on the scheduled jobs in a pipeline. And as a pipeline, we use GitLab CI runner, and some virtual execution environments are created to execute those test cases. And finally, after each execution, we are reporting the results, including the evidences collected during the execution and defects and screenshots and all other attachments to the Jira and X-Ray, which is a plugin of Jira, to manage our test cases. So in this way, we report all of our test results with all details, execution details inside. And mainly, our execution environment is this box you can see in the middle. We develop our test cases in Java language, and of course, we are making use of some frameworks. For example, for the main testing framework, we use TestNG. And for some API cases, we are using Java Jersey client to perform our API request and map the responses. And for UI purposes, we are able to execute our test cases in headed mode and in headless mode as well. So we use Selenium library and Gargoyle software libraries. And for reporting purposes, we use Allure framework as well. And as I told, we are triggering our jobs or pipeline after our deployments, or we are scheduling our jobs for nightly runs, for example. And let's continue with the definition of TestML. A TestML is defined as a weakly designed test case in the literature, which can result in some critical consequences. For example, let's investigate the possible consequences stemming from the TestMLs. For example, when we investigate all the categories, when a feature is working properly, and if our test case is in success mode, in a pass situation, then it's the ordinary situation, this one on the table. There's no problem about this situation. The feature is working as expected, and our test case is passing. On the other hand, if feature is not working as expected, if there's a bug on the feature, and if our test case reports a failure report about this, then it means that we are catching the bug and it's a real bug on the product. The feature is not working correctly, it's not working as expected, and our test case reports the relevant failure to me, to tester. These two are the no problematic cases, but on the other hand, there are some problematic cases. For example, if the feature is not working correctly, but in this case, if our test case does not report a failure about this, then it means that we are not catching the bug, we are missing the bug. And it's a silent error case. And in this case, it means that we are not catching the bug, so we will face the bug in the later stages. For example, maybe after the product is released, and even maybe the customers will report these failures. Maybe we will not eventually catch it, and we will get the bug from the customer. So it's not a desired situation. And maybe on that time when we face the bug, it will be too expensive, and maybe it is not possible to fix, apply our fix on that time, because we could not catch it on time, and maybe it would be too late to apply our fix when we face it. On the other hand, we can have some false alarms. False alarms means that we are getting some failure reports from our test cases, but normally if the feature is working properly, then it means that it is not a real bug. But it's a false alarm. And normally it seems that it is not that risky as the silent error case, because it seems that we are not missing any bug. Even we are getting some more alarms. But indeed, it is as risky as the silent error cases, because we can again some real bugs due to these false alarms. For example, we can illustrate this issue with an incident. In 2005, there was a flight, if I remember correctly, from Prague to Athens, and from Helios Airport Airlines. On that incident, pilots had too many alarms on their screen, and when we investigate the failure reports, they realized that they were all false alarms. And they had a lot of them, and after some moments, they just stopped checking for all those false alarms. And when they had the real bug about the real warning about the internal pressure value in the airplane, then since they already stopped checking for them, they did not catch it, and it resulted in a critical consequence. And what can be a test case? What can be the possible test smell types? Actually, there are maybe more than 100 test smell types defined in the literature. If we make a survey, we can find a lot of them. But on this table, I wanted to get together the most critical ones, or the most common ones, which can be faced most commonly. For example, I created 5 main categories for those. The first is the stability and reliability related issues. The second one is the distortive ones stemming from the assertion errors or mock errors in our automation environment. The next one is scope related issues. For example, if our scope is not sufficient, if our coverage is not sufficient, then it means that we have some scope smells. On the other hand, we can have some overlaps due to the scope issues. And finally, we can have some performance-related issues or structural issues, which means that which are related to the code quality in the test framework. We will go over the most critical ones when I will talk about the solutions that we apply against them. So firstly, let me tell you the story which lies in the background of application of these solutions. Our QA team is responsible for the automation and implementation of test cases. But in some point, we realized that we had too many other tasks apart from implementation. For example, we have some maintenance tasks and we have some analysis tasks. We were having too many test cases which were failing frequently. So we started to think about those, why we had too many frequently failing test cases. And why we had too many analysis efforts. Because of them, we could not find time to implement the test cases which have to be done. So we started to list our problems and test scenarios which are causing these problems, and we started to list the root causes for them. And then one by one we started to develop our solutions against them. So on this table we can see the most problematic cases for us, for our situation. So we collected three major categories for them. The first one is the analysis efforts, blocking us from the implementation tasks. And then we had some escape bugs, which means that there were some bugs which were coming from the customers. And as we discussed, it is not a desired situation in terms of cost and in terms of prestige actually, because no company wants it, because if customers face some bugs, then they may think differently about the product. So, and the final category was the refactoring efforts, which were showing us some weaknesses in our test quality or code quality in our test framework. And as I told, we found some test schemas which were causing these problems. In the previous slide, we discussed that test schemas can conclude in some problems, and these were the test schemas in the second column. And we found root causes for those test schemas, and we developed some solutions against them. Let's continue with our solutions. The first one, against flaky results. The first root cause for the flaky results was the asynchronous waits. An asynchronous wait means a request which does not forward the response properly. I will illustrate this issue with a sample scenario. Maybe it will make sense better. For example, I told that our microservices are working asynchronously. So when I send a request to the cloud, to the product, for a creation request, for example, one of the microservices will respond to my request. And if my request is not in a bad format, for example, if it is not 400 response, or if I'm an authorized people, if it is not 403 or some other bad response, then I'll get a successful response, 200. But it doesn't mean that my request is performed completely, because, okay, the first microservice responded to my request, but maybe on the background the whole operation is continuing. I'm not sure about it. So what I have to do is to assert the expected result after I get the first response. And in this scenario, I try to illustrate this scenario. For example, in the awaiting test code block, I'm sending the request. And in this block, it's just a simulation. What it does is just sleep for 5 seconds, and then the object is created. And what I do in this situation is, after I sent my request, I started to call for the response. In this area, you see. I have a polling interval, and I have a maximum waiting time. After, if the requirement is waiting for 7 seconds as a maximum waiting time, and if the object is not created after 7th second still, then it means it's a failure for me. But until 7 seconds, if it is created in some point, then it means that the object is created and my request is performed properly and the feature is working correctly. Since I do not know after which second it will be created exactly, what I do is calling for the response periodically, and I try to reach to the expected response at some time. And before applying this, we had too many failing test cases stemming from the synchronous weights, stemming from the weight which does not weight properly. And after we apply this, we see that the failing test cases really reduced. And for the same number of executions, we see that instead of having 6 or 7 failures, we had only 1, and maybe we have none of failing cases in some situations. It really helped with the reduction of failing cases stemming from the test code. A second root cause for the flaky tests for the maintenance efforts was the conflicts and the load in the system. And to overcome these conflicts between consecutive executions, we tried to develop cleanup codes. What I mean is, after a test run, if we do not delete all the objects that we create, they can lead to some conflicts for the next run. So what we do is to develop some cleanup codes, and we make use of the after method coming from TestNG framework. And even if in the unexpected failure situations they are triggered, and all the objects which were created up to that point are cleared, and we will not face any blockage or conflict for the next run because of with the help of these cleanup mechanisms. And another thing is test grouping and setting some test suites. Because in some situations we could face some suite dependency issues, which means that if a case cannot be executed with some other cases together in a suite, then it means that we have some suite dependency issues. And in order to succeed this or overcome this problem, we developed annotations and tags inside them, and we get similar test cases together, and we get the test cases together which can be executed in the same suite without any problem. And the last one is test history. On this image, we see the graph of the number of test cases which are passing and which are failing. And with the help of this graph, or with the help of test history, we are able to make a comprehensive analysis. I mean, if we do not have the previous executions, if we have only one execution details in our hands, then we would not be able to make a comprehensive analysis. But in this case, when I have a failing situation, then I could go to the previous executions because I have all the details in my pipelines, and I can check what went there in the previous executions, if it was again failing, or if it was passing that time and failing this time, and I can check what was the change in terms of this test history. And to be able to have a test history, as I told in the beginning, we have to report all of our test execution details after each execution. And this is an illustration of how we do it. By the way, I'm not sure how much are you interested in the codes, but these are all running codes. And if you are interested, you can reach me out for the details of those implementations. But how we do is we report all of our test results at the end of each execution, at the end of each suite run. And for the suite run results, we include all individual test results to the whole list with the status. If the test succeeded, we set the status to pass, and we add these individual results to the whole list. And after the suite run, we send the whole list to the X-ray APIs with the credentials of the users, of course. And our second major category for our problems were the escape bugs. And when we start to think about those, because normally we try to improve our coverage and we try to test all the use cases. But why did we have some bugs coming from customers? When we start to investigate these issues, we realized that some of the customers were using some different environments than we did for our testing activities. For example, we have some hardware modules, which is running in the manufacturing environments. And, okay, we tested the features on the hardwares, but in a limited combination of hardware. Because normally there can be lots of combinations of the operating systems on the hardware. There can be lots of combinations of the versions of hardware. So testing the feature on a limited execution environment was not sufficient. So what we tried to do is to develop some machine manager servers, which were providing us different combinations of all hardwares and supported versions of the execution environments. And for the UI cases, we developed a scenario grid, which supports all possible browsers. And instead of running on a single browser, we included all the possible or supported browsers into the executions. And similarly, when, for example, take into consideration a data upload feature. When we test the data upload feature with an integer value, I still do not know that it will work again with a string value. So here what I do is, instead of executing the test case with a limited data type and limited data values, we constructed a data pool in which all the supported data types were involved. And we include the corner cases and the boundary values as well. So instead of some magic numbers in the code, we use a test pool to use a wide range of test inputs as a test data and test types. And our final major category for the problems are the issues related to code quality in our test framework. And probably the most problematic case for that is the code duplication in the framework. Again, I will illustrate this issue with a sample scenario. On this image, you see there are two Mona Lisa images on the wall. And as a drawer, if I'm asked to change the image, what I will do is, in this case, is I will apply the change on both of them. Because the Mona Lisa image is wanted to be changed, so I should change both of them. But what if I had only one of them? Then my effort would not be doubled. So why don't I do that? I mean, if I have an original image and I reflect this image on various points, then when I'm asked for a change, I will apply the change on the single point of usage, and the change will be reflected to all point of usages. And in the code, what they did is a similar manner. I mean, these on the top of the image, these are the code to create some entities. And for most of the cases, first we create some entities and then proceed with the further steps. Then, why don't we get move this to a method or a class in another point and then call them? And we created some helper classes for this, and in the helper class we collected those repeatedly used methods or blocks, and we just call the relevant helper class in a single line. And you see that the understandability and the readability and maintainability of the code is really improved in this situation. And another way to improve the code quality is, of course, peer reviews. After we develop code, each piece of code, we send it to merge requests, and another colleague in the team is reviewing it, and with the help of a second eye, we detect some weaknesses in the code, and we try to improve the code quality. And another way of doing this is to get help from the tools as well, in addition to the colleagues in the team. For example, we integrate SonarQube in our pipelines, and it detects some vulnerabilities and weaknesses in the code. And after we run our pipelines, the analysis is being performed, and we collect the weaknesses and vulnerabilities from the report of the SonarQube. And after we fix them, we run the pipeline again, and they are merged after everything is fixed. So these were the three major categories, three major titles for the problems and the solutions for those. And now I want to talk about some other supportive automation actions. For example, the first one is to track the issues or bugs, for example. We can make some queries over Jira automatically from the code. For example, on this one, what I do is to perform some queries which looks very similar to how we do it on the Jira dashboard on UI. And after I perform this query over the Jira API, I get the response, and I can check the creation date of the issue and the resolution of the issue as well. And I can measure the duration between the creation and the resolution of the issues. So I can make some insights about the resolution times of the issues. Then, so this is a way to automatically monitor and track what's going on about the issues that I create on Jira. Another one is making use of S3 buckets. For example, for our test cases, we have some test inputs and test outputs, and we do not want to lose them. For example, in some test cases, we are using test files to upload them. So keeping them, storing them locally is very difficult. So what we do is to make use of these Amazon S3 buckets, and we can download the test inputs before the execution, or afterwards, after each execution, we can upload our evidences to the buckets, not to lose the evidences related to the executions. For example, in this case, it's just an example for a UI case, and when a UI case is failing, then we capture the screenshot about the failure point on the UI, and we upload it to the S3 buckets over the S3 clients that we develop in our framework. And finally, visualizing what's going on in our processes is very important, I think. And to making some dashboards makes you be aware of what's going on about the processes. For example, in our case, the asset counts on the environments are very important. So what we track in this graphs were the asset counts in our environments, and how we can do this is to make use of the Amazon CloudWatch service or some other monitoring tools, for example, Grafana, or there are lots of variations for those purposes. But what I want to tell is we can make use of automation for all these steps. Instead of manual efforts, we can upload all our data to the cloud or to some other environments over our test code in the test framework, and we can manage our process automatically instead of manual efforts and cost issues. So again, this is the same slide that I showed in the beginning. So again, I want to remind this you. This is just like a summary of this talk. These were the problems that we faced in our test framework, and they were stemming from the test smells. So as a short summary, what I wanted to try is to make awareness on the test smells and possible solutions, problems stemming from them. And okay, there are a lot of test smell types which can appear in any automation environment. There are maybe 100 types of test smells. It looks scary, but of course we can do something against them, and we can develop some solutions against them. So as a final sentence, my call for action is be aware of the test smells which can appear in automation environments, and develop your own solutions to reduce the maintenance efforts and costs in your environments. Thank you.
We've got some questions. So, while Patrick organises the plugging in, any questions, direct questions?
Okay. Thank you for your talk. One question regarding the test automation stuff. Are you testing your microservices only from the GUI, or you are using also some kind of automated tests that you directly, more or less, attack the microservices?
Actually, for our QA team, we are performing our test cases in the end-to-end level. And there are some other tests that performed in the development teams as well. Our QA team is a separated one. So the test levels are performed in different teams. So as a QA team, what we perform is the end-to-end cases. And normally we perform our test cases in a black box approach. So normally we don't go over the microservices, but the whole product. And not only in GUI, but we are performing some API requests as well. But as I told, we are not going over each microservice, but just the features of the products as a whole.
So, and if your development teams are testing on integration, maybe behind two microservices, then which tool they are using there?
I'm not sure if they are using any specific tool,
Okay.
but they are using contract-driven testing
Okay.
and some other approaches, but I'm not sure if they are using any specific tool for that.
Okay, thank you.
Okay, on the Slido, the question, do you use any test coverage technique product to measure how much of tested app is covered by your test?
Yeah, actually this is another common question for the test coverage. Actually, we do not use any tool to measure this coverage, but what we do is to measure the coverage against requirements. Normally in each release or in each deployment, we map our test cases to the requirements which are being developed, or in terms of regression testing. So we are trying to cover all the requirements with the test cases.
Okay, any more questions? Okay, so Mesut, thank you very much.
Thank you.
Thank you.